Vanilla flavor chemistry. From orchid pods to the world's most important flavor molecule. Vanilla is one of the most widely recognized and economically important flavor ingredients in the world. It originates from the tropical orchid species Vanilla planifolia, native to Mexico, and is the only orchid extensively cultivated for human consumption. The characteristic aroma of vanilla is not present in freshly harvested green pods. Instead, it develops through a complex curing process that transforms odorless precursors into a rich mixture of volatile compounds. At the center of this transformation is vanillin, 4-hydroxy-3-methoxybenzaldehyde, the principal compound responsible for the familiar sweet, creamy, and warm vanilla aroma. Today, vanillin is the world's most important flavor molecule, finding applications in foods, beverages, fragrances, pharmaceuticals, and advanced materials. Its history illustrates the intersection of agriculture, chemistry, biotechnology, and global commerce. Historical development of vanilla and vanillin. The cultivation and use of vanilla dates back over 1,000 years in Mesoamerica. The Totonac people of present-day Mexico were among the first to cultivate vanilla, and later the Aztecs used it to flavor cacao beverages consumed by nobility. When Hernán Cortés arrived in Mexico in the early 16th century, vanilla and chocolate were introduced to Europe, where both rapidly gained popularity. For centuries, vanilla remained a rare luxury spice. A major challenge was pollination, as the vanilla orchid depended on specific native bees found only in Mexico. Commercial cultivation expanded dramatically after the development of hand pollination techniques in the 19th century, enabling production in tropical regions such as Madagascar, which is now the world's leading producer of natural vanilla. A landmark achievement in flavor chemistry occurred in 1858 when Nicholas Theodore Goebli isolated vanillin from vanilla extract. Subsequently, German chemists Wilhelm Hamann and Ferdinand Tiemann elucidated its structure and developed the first industrial synthesis in 1874. Their work marked the birth of the synthetic flavor industry. Chemistry of vanilla flavor. Natural vanilla is far more complex than vanillin alone. More than 200 volatile and semi-volatile compounds contribute to its aroma profile. Important constituents include vanillin, p-hydroxybenzaldehyde, vanillic acid, anisaldehyde, guaiacol, acetovanillone, and numerous phenolic and furan derivatives. Vanillin typically represents approximately 1 to 2% of the dry weight of cured vanilla beans and is responsible for the characteristic sweet, creamy, balsamic, and slightly smoky aroma. However, premium vanilla extracts derive their complexity from the synergistic interaction of many minor compounds. Consequently, pure synthetic vanillin cannot fully replicate the depth and richness of natural vanilla extract. The molecular formula of vanillin is C8H8O3, and its structure consists of an aromatic benzene ring containing 3 functional groups: an aldehyde-CHO, a methoxy-OCH3, and a phenolic hydroxyl-OH. This combination gives vanillin its distinctive odor, moderate water solubility, antioxidant properties, and chemical versatility. Formation of flavor during curing. Fresh vanilla pods contain little free vanillin. Instead, they store flavor precursors primarily as glucovanillin, a glycosylated compound lacking the characteristic vanilla aroma. The traditional curing process consists of several stages: harvesting mature green pods, blanching in hot water to stop metabolic activity, sweating under warm conditions to activate endogenous enzymes, slow drying and conditioning for several months. During curing, beta-glucosidase enzymes hydrolyze glucovanillin, releasing free vanillin. Simultaneously, oxidation, esterification, and other biochemical reactions generate the complex bouquet associated with cured vanilla. The process transforms green, odorless pods into dark brown beans rich in aromatic compounds. Different producing regions employ distinct curing methods, creating unique flavor profiles. Madagascar vanilla is known for its creamy sweetness, while Mexican vanilla often exhibits spicier and woody notes. Sources and production of vanillin. Natural vanilla. Natural vanillin is extracted from cured vanilla beans. Despite its premium status, natural vanilla accounts for only a small fraction of global vanillin consumption due to limited agricultural production, labor-intensive cultivation, and price volatility. Synthetic vanillin. Growing demand led chemists to develop alternative production methods. Historically, vanillin was synthesized from eugenol obtained from clove oil. Later, lignin derived from sulfite pulping waste became a major industrial feedstock. Today, most synthetic vanillin is produced from guaiacol and glyoxylic acid through a two-step process involving electrophilic aromatic substitution followed by oxidative decarboxylation. This route provides high yields and consistent quality at relatively low cost. Biotechnological production. Modern biotechnology has introduced natural vanillin produced through microbial fermentation. Ferulic acid obtained from agricultural materials such as rice, bran can be converted into vanillin by engineered microorganisms. These processes satisfy consumer demand for naturally derived ingredients while reducing dependence on vanilla bean harvests. Occurrence beyond vanilla. Although vanilla beans are the richest natural source of vanillin, the compound occurs in numerous foods and beverages. Small quantities are found in butter, coffee, maple syrup, olive oil, raspberries, lychee fruit, oak-aged wines, and spirits. Thermal processing can also generate vanillin through the degradation of lignin and related phenolic compounds, contributing to the flavor of roasted foods and beverages. Applications in flavor and fragrance. Food and beverage industry. Approximately 3/4 of vanillin consumption occurs in food applications. It is widely used in ice cream, chocolate, bakery products, confectionery, dairy products, beverages. Vanillin possesses powerful flavor-enhancing properties and can mask bitterness in cocoa, protein supplements, pharmaceuticals, and nutraceutical products. Fragrance and personal care. In perfumery, vanillin is classified as a warm gourmand note. It contributes sweetness, depth, and persistence to fragrances. Vanilla accords are common in oriental, amber, gourmand, and floral compositions. Vanillin is also incorporated into soaps, lotions, shampoos, deodorants, lip care products. Its pleasant aroma and mild antimicrobial activity increase its value in personal care formulations. Pharmaceutical applications. Vanillin serves as both a flavoring agent and a chemical intermediate. It improves patient compliance by masking unpleasant tastes in oral medications and is used in the synthesis of various pharmaceutical compounds. Emerging applications in sustainable materials. Recent research has expanded vanillin's role beyond flavor and fragrance chemistry. The molecules aldehyde, hydroxyl, and ether functionalities make it a versatile, renewable building block for polymers, epoxy resins, adhesives, and bio-based plastics. Vanillin-derived polymers have attracted considerable interest as sustainable alternatives to petroleum-derived materials. Researchers have demonstrated vanillin-based epoxy systems with excellent mechanical properties and reduced environmental impact. Safety and regulatory status. Vanillin has a long history of safe use and is generally recognized as safe for food applications when used at approved concentrations. Toxicological studies indicate low acute toxicity, and regulatory agencies worldwide permit its use in foods, cosmetics, and fragrances. Natural vanilla extracts may contain additional compounds that contribute to allergenic potential, but vanillin itself exhibits an excellent safety profile. Ongoing research has also investigated antioxidant, antimicrobial, anti-inflammatory, and potential chemoprotective activities, although many of these findings remain under scientific evaluation. In conclusion, vanilla represents one of the most remarkable success stories in flavor chemistry. From its origins in ancient Mesoamerican civilizations to its central role in modern food, fragrance, and biotechnology industries, vanilla has maintained its status as the world's favorite flavor. While vanillin is the dominant aroma compound, the unique sensory complexity of natural vanilla arises from hundreds of interacting molecules formed during curing. Advances in synthetic chemistry, biotechnology, and sustainable materials science continue to expand the applications of vanillin, ensuring that this iconic flavor molecule remains indispensable to both industry and consumers.